Hello everyone. I'm Sayog Varan Pata from the BSc Honors Data Science and Artificial Intelligence program at IIT Guwahati. In this video, I'll be presenting my internship project titled EV Forecasting Dashboard, a machine learning approach for county-level electric vehicle adoption prediction. The objective of this project was to develop a machine learning system capable of forecasting future electric vehicle adoption trends using historical EV registration data and deploying those forecasts through an interactive dashboard. Rather than simply analyzing historical data, the goal was to predict future EV adoption and provide insights that could support infrastructure planning and policy decisions. As electric vehicle adoption continues to grow, governments and utility providers need reliable forecasts to plan charging infrastructure, grid expansion, and transportation investments. While historical EV registration data is available, it cannot directly answer questions such as how many EVs will be adopted in the future, which counties are expected to grow the fastest, and how should future infrastructure be planned. Therefore, the objective of this project was to build a forecasting system capable of predicting future EV adoptions trends at the county level using machine learning. For this project, I used the electric vehicle population dataset obtained from the Washington State Open Data Portal. The dataset contains information such as county, state, date, battery electric vehicles, plug-in hybrid electric vehicles, and total electric vehicles alongside total vehicles and percent electric vehicles. I selected this dataset because it provides historical EV adoption information across multiple counties, making it suitable for forecasting future growth. The dataset contains both numerical and categorical features. Before model training, preprocessing was required to ensure the data was clean, consistent, and suitable for machine learning. The first step was converting the date column into date-time format. This was necessary because machine learning models cannot directly interpret date strings. Converting dates allows us to extract meaningful time-based information later during feature engineering. Missing target values were removed because incomplete target information can negatively affect model training. For county and state values, missing entries were replaced with unknown instead of removing the record. This helped preserve useful information while maintaining dataset consistency. I also performed outlier detection using the interquartile range method. The reason for handling outliers is that extreme values can distort model training and lead to unstable forecasts. Instead of removing those observations entirely, I applied outlier capping to reduce their impact while preserving the underlying information. Feature engineering was the most important stage for this project because forecasting model depend heavily on the quality of input features. Machine learning models do not automatically understand trends or time progression, so meaningful features must be created. I first extracted year and month information from the date column. This allows the model to recognize seasonal and temporal patterns in AV adoption. County names were encoded using label encoding because machine learning algorithms require numerical input rather than text values. Next, I created lag features representing EB count from 1, 2, and 3 months earlier. These features are important because future EV adoption is strongly influenced by recent historical adoption patterns. I also created a rolling mean feature using the previous 3 months. The purpose of this feature was to smooth short-term fluctuations and capture long-term trends. Growth rate features were also created. Rather than only looking at EV counts, growth rates help the model understand whether adoption is accelerating or slowing down. Finally, I calculated a 6-month growth flow using polynomial fitting. This feature measures both the direction and speed of EV adoption. For forecasting, I selected random forest ratio. I chose this model because EV adoption patterns are often non-linear and influenced by multiple interacting factors. Random forest handles non-linear relationships effectively and performs well on structured tabular data and is resistant to overfitting. To improve model performance, I used random search DB for hyperparameter training. This automatically evaluates different parameter combinations and identifies the configuration and produces the best result. For the trend test split, shuffling was disabled. This is important because forecasting problems must preserve temporal order. The model should learn from the past and predict the future, just as it would in a real-world scenario. The model was evaluated using three metrics: mean absolute error, root mean squared error, and R squared score. MAE measures average prediction error. RMSE penalizes larger errors more heavily. R squared measures how well the model explains variation in the data. The model achieved very strong performance with an R squared value close to 1. While comparing actual and predicted values, we can see that the model closely follows historical EV adoption patterns. Future importance analysis revealed that lag features and growth related features were the most influential predictors. This confirms that recent EV adoption history is the strongest indicator of future EV adoption. After training the model, I built a recursive forecasting system capable of generating forecast for the next 36 months. The model first predicts the next month. That prediction is then fed back into the system and used to generate the following month's prediction. This process repeats until a complete 3-year. The final stage of the project was deployment. I developed an interactive template dashboard that allows users to select a county and generate a 3-year EV adoption forecast instantly. In addition to forecasting monthly values, the dashboard also visualizes cumulative EV adoption trends, making long-term growth easier to interpret. The dashboard also supports multi-county comparison, allowing planners to evaluate projected EV adoption trends across multiple regions simultaneously. To conclude, this project successfully developed an end-to-end machine learning forecasting pipeline for county-level EV adoption prediction. The project involved pre-processing, feature engineering, model training, forecasting visualizations, and deployment. One of the key findings was that recent EV adoption history and growth trends are the strongest predictor of future EV adoption. The final dashboard transforms this forecast into an accessible decision support tool that can assist planners, policymakers, and infrastructure developers. Thank you for watching.